Okay, so Francesco, you have the pleasure to end this afternoon.
Thank you very much for the introduction. Thank you for the invitation. It's a real pleasure to be here. I really thank the organizers. Today, I want to talk about this quite recent paper done in collaboration with the Turin group, which is about the strong coupling of N=2 superconformality theories in the context of holography. So we can start. If you have any questions at any time, just ask without any problems, also before the end of the talk. So the general context is the SCFT, and we know that Maldacena realization represents a definitely milestone in this holographic context. It relates some supergravity theory on ADS5 cross S5 background with a 4-dimensional N=4 super Young Mills at strong coupling. And one of the crucial points of this configuration is that the symmetries of N=4 super Young Mills allow for some exact results in the strong coupling lambda, which is the usual Toft coupling. Let's show an example of this fact, which refers to this paper of 1998, quite famous, the 3-point function of chiral operators, which is a special observable. We will define it in a better way later. It's very special because it has no quantum corrections. And this means that we can compute it on the gauge theory side using simple Feynman diagrams computations, and it has just the 3-level contribution. And the 3-level contribution at this point is equal to the strong coupling limit. And this means that we can, at this point, match with the cubic term of the supergravity action on this ADS5 cross S5 background, as represented in this sketchy picture here. And the question that I want to address in this talk is, what about the less symmetric N=2 superconformal case? Is it still possible to obtain something similar? Well, in general, it is harder to find exact results in this context, but we will identify special theories where we can obtain some exact results for special observables and match them with a supergravity side, like it has been done in this N=4 case. Okay, these are the theories we are going to deal with. They can be described as a family of N=2 theories, which arise as ZQ orbifold of N=4. So we start from the N=4, which has this special quiver shape. And using this ZQ orbifold, we obtain this theory, which is represented here as a quiver with the Q nodes, where each node corresponds to an N=2 vector multiplet, which is in the adjoint of an SUN gauge group, while each edge corresponds to a hypermultiplet, which is in the bifundamental of 2 neighboring gauge groups. These theories are special because they enjoy an explicit Lagrangian formulation, and they admit also a sort of holographic dual, which is of type ADS5 cross S5 quotiented over ZQ. And these 2 things will be important in a moment. In this theory, in this general N=2 context, let's say, we want to study these physical observables, which are chiral primary operators, which is an important class of operators, as I said. They are defined as gauge invariant quantity, like this formula here, trace of phi to the n, where phi is the scalar field of the vector multiplet. They are special since they are 1/2 BPS, so they are protected by supersymmetry, and in particular, their conformal dimension is fixed to be equal to the arc charge over 2. And most importantly, they enjoy this chiral ring structure, which means that their OPE is non-singular. And if we choose this coefficient C in the following way, with this delta function, this means that this 3-point function, which is chosen in a special way in order to preserve U1 charge, can be secretly written in terms of a two-point function of this type. And this is something that have been developed in a series of papers between 2014 and 16. In our context, we are in quiver theories. We have multiple vector multiplets. So we have many of these chiral primaries. And so for this reasoning, we can concentrate on the following two-point function. This is fixed by the usual conformal symmetry to be of this shape. And we are going to try to compute explicitly this two-point coefficient. And as we said before, this has a strong physical meaning. How can we compute this G function? The mathematical tool is supersymmetric localization, which is, I mean, it was also mentioned before. It is a very special tool in this n equal to 2 context. And the idea is simply the following. The path integral is mapped to a four sphere starting from a Euclidean four-dimensional space, and using supersymmetry charges is reduced to a finite dimensional integral. So we end up with an integral over S4, which is written in terms of a matrix of n by n dimension. Now, in the maximally supersymmetric case, n equal 4, this matrix model is extremely simple, is simply Gaussian, and this explains why we have these exact results in the n equal 4 settings. Instead, in our case, the ZQ orbifold partition function is reduced to a Q multi-matrix model, since we have Q nodes of this kind. Still, we have some Gaussian term like this, but also special interactions, which have this shape. This is not important how they look like. The important point is that now, having this partition function, we can explicitly compute observables using this matrix model. And let's say we can explicitly compute our two-point function in terms of Gaussian integral techniques, which have been developed in a series of papers between 2017 and 2020. And here we see an example of this kind of procedure for, I mean, this two-point function for Q equal 4, so 4 nodes, and for operators with conformal dimension 2. We see there is a huge perturbative expansion labeled by this Riemann zeta function. But now the question is, can we go beyond perturbation theory? Because we wanted to obtain some exact result also in this n equal to 2 context. And so the trick, let's say, is to consider special combinations of these chiral operators. So we can define untwisted and twisted operators in this following way. So we have untwisted combination, which are simply sum of these operators, and the twisted combination, which are Q minus 1 possibilities, are labeled by the Q root of the unity, which is this row. And for example, for the 2 nodes case, we have just a single twisted operator. So the difference is quite simple, just this minus sign here. And these combinations enjoy special properties. First of all, they are simply orthogonal to each other, and this will be important in a moment. But also they are the right observable for holographic purposes, since they are coupled to untwisted and twisted closed string states on this IDS5 across S5 over ZQ background. And we will see how. At this point, with these new observables, we can rewrite our partition function on S4 using this change of variables. We obtain this formula. Again, the explicit shape is not important at all. I just want to stress this factor S alpha here, which stands for this sin square, which depends on our model we are considering. And since here we have just twisted combinations, due to these orthogonality properties mentioned before, we immediately find that the untwisted two-point function precisely follows the n equal 4 result. So for the untwisted combination, we get the same planar result as the n equal 4. And this is clearly exact as the n equal 4 was. Instead, if we consider the twisted sector, in any case, we see that this interactive action is quadratic now for these T alpha variables, for this twisted combination. So we can rewrite our matrix model as this effective Gaussian integral in terms of these infinite dimensional vectors. And we can formally resolve this, new model in terms of this determinant, where now this X matrix contains the full dependence on the coupling constant lambda. It has this shape, which is written in this, let's say, integral representation. And now we can explicitly compute this two-point function, solving this Gaussian integral for the twisted combination as well, obtaining this ratio of these two determinants. And this is also for this n equal 2 context, some exact results in the coupling lambda. At this point, we can expand this expression for strong coupling, lambda going to infinity, using Mellin transform methods, and we get this explicit result. Let me stress here this peculiar coupling dependence, 1 over lambda, and also we see again this sin square factor, which takes into account our model we are considering, and this dependence over the conformal dimension. So finally, I just conclude by saying something about the holographic perspectives of these quantities. The idea is that we want to match these strong coupling results with the supergravity on this ADS5 process 5 over the cube background. And we saw that these untwisted states, which are dual to the untwisted operators, of course, have the same behavior as the n equal 4. So no problem from that. Instead, due to these orbifold singularity, the dual twisted states live on this ADS5 process 1 part of the total background. And this has been developed by Bukov in 1998. At this point, if we compactify over this S1, we can extract this quadratic part of the supergravity action, and we see that the part containing these dual twisted states precisely contains our coefficient, which we got from the two-point function from the dual gauge theory side. And so we see that this normalization perfectly matches our strong coupling result. And for the future, the next step in this SCFT setting in, let's say, in equal 2 theories is that we would like at this point to complete this three-point function match, which means adding here also the three-point function, so the cubic coupling for these twisted terms. I would also like to go beyond this protected spectrum, because this comes from the twisted operators, which were 1/2 PPS. So we would like to go beyond this limit and also try to explore different equal to theories using similar techniques, so localization, field theory techniques, and so on. With this, I thank you for the attention, and I can stop here. Question.
Okay, I start. Let me ask you about integrability. So, what is the expectation there when you model out by the integrability? Is it normal to deform the?
Well, I'm not an expert at all on this, but I feel like, I mean, I've spoken to some guys that suggest that since these special theories do have some holographic duals, so they are quite similar with respect to n equal 4, there could be some integrability approach. And for sure, there would be, I mean, it would be definitely interesting to explore something similar. For sure, it would be important to explore this protected spectrum for the n equal 2 settings. And I don't know whether there is something too explicit that has been done. I know there are some papers by Castelli, Pomoni in quite recent years, but I don't know whether there is something more than this. So,
other questions? I don't know if Nicholas wants to make a comment about this question. Okay, I guess we are all tired after a long day of talk.
yes.
So thank you very much, Francesco.
Thank you.